Um, so far in this chapter, you've learned how to find confidence intervals, which basically means a range of scores that you can use to estimate either an average or a percentage. Today, we're going to look at the question of how big of a sample do you need to get the results that you want? We're going to look at what we call sample size problems. And it turns out that in statistics, there are always three things that kind of play against each other, which are the confidence level, the margin of error, and the sample size. If you change any of those things, it's going to like tug on the others and change them as well. If I wanted to have like really, really high confidence, I never want to be wrong in my estimation, then either I'm going to have to widen that margin of error so that I include more stuff, or I'm going to have a really, really big sample so that I can make sure that I'm more confident with things. If I want to have a little teeny tiny margin of error, then I either need to be willing to be wrong a bunch of the time and have a smaller confidence level, or I'm going to have a really big sample. And if I want to get away with a small sample, then either it requires a big margin of error or a low confidence level. So if you change any one of those, the others have to change along with it. In an ideal world, you want the confidence level to be as high as possible and the margin of error to be as low as possible. If everything were perfect, you would want to be right on the money with zero margin of error, and you'd want to be 100% confident. Now, that's never going to happen in the real world, but you certainly want to be as close to those two things as you can. And in fact, in jobs, it sometimes is your boss that sets those. They say, this is what needs to happen. You need to be this close, and you need to be 99.9% confident. Make it happen. And what you've got to do is figure out how to make it happen. And the only thing you can actually change is your sample size. If you have a big enough sample, you can pretty much get any confidence you want and any margin of error you want. In fact, if you literally did want to be 100% confident and zero margin of error, what you would do is take a census. You would literally ask everybody or look at everything, and then you'd have those results. You almost never have the time or money to take a census, though. That's the problem. And so the question ends up being, how many is enough? Because the more things you look at, the more people you ask, the longer it's going to take and the more expensive it's going to be. So you want to keep things reasonably small, but it's got to be large enough that you get reasonable results. And that's what we're going to end up looking at. Basically, what this is going to boil down to from your point of view is two formulas that'll tell you how big a sample you need to get the results that you want. We're going to look at one formula that deals when we're trying to estimate averages and another one when we're trying to estimate percentages. These are not built into the test menu in your calculator, so you do need to actually plug numbers into these formulas. When I was going through these with Joey and Eric yesterday, they were asking, do we have to memorize the formulas? No, you don't, but you will need to understand how to use them. And here's the first of them. It's what I use if I want to find out how many I need in a sample and I want to estimate an average. And you notice it says ZC times S over E squared. So there's a bunch of stuff going on there. But at least one of those things, you already know what it means. What's S always stand for when we're doing any sort of problem that deals with like averages and stuff? Standard deviation, yep. And S is indeed standard deviation. E is the margin of error. When you're looking at a story problem, the dead giveaway for margin of error is the word within. It'll say like, we need to estimate this within 1 ounce or whatever. It'll just give you an amount that you have to be within, and that's your margin of error. ZC, when I was looking at that formula yesterday, Joey said, oh God, we still have to do Z stuff. And You can probably kind of hear him saying that actually, but yes, you do, although it's really quite a bit easier than what you did in the last chapter, because if you dig out your Z table and you look at the side of the Z table that I called the big table, you'll find that there's a little inset at the bottom left of that table that looks like what I have up on the screen there now. And what this is telling you is the Z-score that you need for these problems. This is actually based on, you might remember some problems that you did earlier where it showed you a bell curve and it said find Z so that like 95% is between negative Z and positive Z. And you're supposed to fill in the middle. The way you did that then is you realized, well, if 95%'s in the middle, then 5% would be on the outside, which means each side was 2.5%. And what you did is you looked up like 0.025 in the table and found out what the Z-score was that went with that. It turns out that here, they've already done that for you, and for 95%, the answer is 1.96. And in fact, they could give you any level of confidence at all, and you would look up the Z-score that goes with it. The three that you pretty much ever use are 90, 95, and 99, but in theory, you could use any of those numbers. And that's what you're going to plug in that place in the formula where it says ZC. Okay? So ZC, the Z-score at the level of confidence, times the standard deviation divided by the margin of error squared. Now you might remember at the beginning of the chapter when I went through and talked about like finding margin of error, I sort of fast forwarded in the notes past a formula then that I said you didn't really need to know because it was built into your calculator. All that formula I just looked at is the exact same formula, but it's solved for n instead of e. And that's really all that's going on there. You do, however, need to actually plug into that formula because it's not built into the test menu on your calculator. So you do have to do it. I'm not honestly quite sure why it's not built into the test menu, because honestly, I could write a program that would do that, but the people at Texas Instruments didn't. So you do have to actually do it. So a typical problem might look something like this. We have a battery manufacturer who wants to know the average time their AAA batteries will last when used in calculators. They tested 16 batteries in conditions similar to calculator use, and they find that they lasted 13.7 hours with a standard deviation of 1.9. And then it says how many batteries will they have to test to estimate the actual average within 0.5 hours with 99% confidence. I'm going to go back to that first screen for a minute, because on this first screen, there is actually only one number that matters for this problem. 1.9, yeah, we've got to know the standard deviation. Nobody cares about the average, though, and nobody cares about how many they've tested so far. All we really care about is the standard deviation. So 1.9 is the standard deviation. I do need to know the within, because that's the margin of error, is 0.5 hours, half an hour. And I do need to find the Z-score that goes with 99% confidence. So who can tell me, what is the Z-score that goes with 99% confidence? 2.58. So what I'm going to do then is I'm going to take those numbers and we're going to plug them into the formula. I'm going to take 2.58 times my standard deviation, 1.9, divided by 0.5, and I need to square all of that. I either take it to the second or I hit the x squared key. And Meredith looks like she's been doing that, and hopefully she also got like 96 and some change. Okay. Single most important thing on all of these problems is that when you're doing problems like this, you always, always, always round up. I purposely did this problem so it came out to 96.1. The answer to our problem is 97. You round up to the next whole number. That's because you can't do 0.1 batteries. Yeah, it's literally impossible to test that. If I only did 96, it wouldn't be quite enough to get the results I need, but if I do 97, it's going to be more than enough. So 97 is what we would have to go with for our answer. So do you guys get how that formula is working? Again, we do the z-score I look up in the table, times the standard deviation, divide by the margin of error, and then square it. Okay? Any question with just that much so far? As I go through the rest of these. So we're actually going to spend a little bit longer on the second of the two formulas. It's not a hard formula, but we are going to spend just a little bit longer doing it. It's what we use for percent or proportion or binomial problems. This would be like trying to predict the election, how many people that they need to actually poll in a state to get an accurate answer. That's the kind of question. It says here, if I have an estimate for P ahead of time, the formula looks like this. And it looks kind of weird. It says P hat times Q hat ZC over E squared. Well, the stuff in the parentheses, you actually should already know, because the ZC is just the same z-score I look up that goes with a certain level of confidence, just like I did before. E is still the margin of error. That's not going to be any different. The P and Q at the beginning, what that is the percent that do have whatever characteristic I'm talking about and the percent that don't have the characteristic I'm talking about. Like, what percent of people do we think do support a certain candidate? What percent of people don't support a certain candidate? Those two numbers should always add up to 100% or to 1. So you can, if you know P hat, you can always find Q by just subtracting from 100. That'll end up giving you that. And you do always enter those as decimals. We'll get to that when I actually work out the formula here in a minute. Again, E is the margin of error. That's also a decimal. And I look up the confidence level. The other thing it says here, and this will make more sense when we look at a couple of problems, is if I don't know that ahead of time, I just assume that P is 50, that if this is a 50-50 situation, and I'd actually work out the formula like this. That's because 50-50 is the worst possible thing that you can have happen. All of those states they didn't call until a week after the election was over, or almost. They did that because the margin of victory was so close it all but was 50-50. Now in Georgia, they're literally doing a manual recount where they're going through and literally tallying all the votes by hand. And that's because out of millions of votes, it was like, I think it's right at 10,000 was the final victory margin they had there. So somewhere in that range, which is pretty darn close. That's the sort of situation where it's really hard to predict a winner. If it's like 70-30, well, I know what's going to happen. I just need to know the final numbers. Okay. So we're going to look at probably 3 examples here. Here's the first one. It says, in the first games of the season, the players on a basketball team made 8 out of 11 free throws they attempted. A sports analyst wants to predict the team's free throw percentage for the whole season. And the question is, how many attempts will have to be analyzed to estimate that within 10% either way with 90% confidence? So I'm going to go back to this. First thing I want to know is what's 8 out of 11 as a percentage? %. Okay, so that means they're making 72% of the shots they take from the line so far. What that is the P hat. That's that first number that goes in there. Well, if they make 72% of their shots, what percent are they missing? 28. Yeah, that's the Q hat, right? Those are those two numbers that go at the beginning. We're supposed to do 10% margin of error, so the E is going to be like 0.10 or 0.1. And we have 90% confidence. What's the z-score that goes with 90% confidence? 1.645, okay. So we're going to use those to work out our answer here. And I actually did p-hat as 0.73 because I believe it does actually round up to 0.73 and then 0.27 here. So if you do work those out, I'm pretty sure we're going to get something that rounds up to 54 shots they're going to have to analyze to find a good estimate for that. Everybody follow that okay? Something that's important in that formula is that it's just the parentheses that are squared. It's not p-hat and q-hat. And in fact, when people miss it, that's the most common mistake they make is they try and square the whole thing, which is what it was in the average formula, but here it's just the end that ends up squared. So let's look at another couple of examples here. We got some people that are running for governor. Preliminary poll shows that 57% of the voters favor Mr. X. How large of a sample should they take to estimate within 2% either way with 95% confidence? So what's the z-score we need this time? 95% confidence. 1.96, okay. And I'm pretty sure 0.57 is going to be the p-hat. Can anyone tell me what the q-hat would be? 43, yeah, which means that what I want to do is throw these different numbers in there, 0.57 times 0.43, and then 1.96 over 0.05 squared. And again, your answer should always be a whole number, and you should always round up. This time you would round up anyway, but it is going to end up being like 2,354 people. Typically, 2,000 to 3,000 is what a lot of major polls are doing. That is very typical for a number they might use for that. And I got two more questions we'll take a quick look at. The Des Moines Register is trying to figure out the percentage of Iowans who support Governor Reynolds. I think in your notes it may say Governor Branstad, but same thing. They don't have a previous estimate of what the rating should be. So how many people should they sample to be within 4% of her actual approval with 95% confidence? So what did I say we do if we don't have an estimate ahead of time? We assume it's 50-50, right? So I'm just going to do 0.5 times 0.5 times 1.96 over 0.04. The 1.96 is just the confidence level or the z-score that goes with 95% confidence. And looks like 601 people ought to do it. Everybody follow where that's coming from. And the last one, you have no clue what percent of people shop at Walmart. I don't either, although I'm betting it's more than 50%, but that's beside the point. Question is, how large of a sample should you select to estimate this within 3% either way with 99% confidence? This is one that also may actually be wrong in the written notes, but we're going to talk about it here. So it says 99% confidence here. What's the z-score that goes with 99%? 2.58, right. Which is why I'm pretty sure that what we would want to do with this is 0.5 times 0.5 times 2.58 over 0.03 because we want to estimate within 2% squared. And this one happens to literally come out even. And if it does come out even, that's the number you need. You don't need to go up to 1850. Not that it would make a huge difference, but that is what you'd end up with. So any questions you guys have on how to find the number that you need? What we're going to do is give you some problems